Okay, so let's do practice quiz 7, number 2. It says let R be the region in the first quadrant outside the circle x squared plus y squared equals 1 and inside the circle x squared plus y squared equals 2 squared. By changing variables to polar coordinates, find this double integral here. So I've graphed the region they're talking about. This top guy here is a unit circle, so it'd be all the way around like that. But it says in the first quadrant, so I'm just restricting the unit circle to the first quadrant. So it's from here to here. And this guy over here would be a circle of radius 2, so it'd be all the way around like that, but restricting to the first quadrant would be just this part of it here. So pretty much the x and y would have to be positive. So the region's between them, so it's in here. So it says by changing variables to polar coordinates. Well, first note here, so if I pick a point here, that you can think of as x squared plus y squared equals r squared. It would pick up another circle in here. But I need the r to be between 1 and 2. So if r varies between 1 and 2, it'd pick up different circles inside there. It'd pick up all the region in. So we're going to say let x equal r cosine theta, and then a y equal r sine theta. So making those substitutions then, well, actually let me move them over here a bit more. Actually, well, I'm going to put them up here actually. So we're going to have let x equal r cosine theta and y equals r sine theta. If we did that, then it's going to our S region, I claim, we'll kind of explain that in a second here. The S region will be over here, say. So the R, let's do the R down here. R will go from 1 to 2. This would be R here. And theta would go from, well, you want to be in the first quadrant, so theta would have to go from 0 to pi over 2 to stay in the first quadrant. So pi over 2 up here. It's your theta axis here. So it would look like this, I claim, our S region. So in particular, let's take this away for a second here. Put our R out over here. Actually, I'm going to move my S out over here too. That's my S right there. We can find a mapping between them. Let's call it T. So I claim making the substitution for x and y will map this rectangular region into this over here, this region R. So let's take a look. For example, if I went here, say, let's do dotted. I claim that guy would map into this. So, and if I went another one, say here, that map to something like this. And this guy here would map, so that one right there would map to that. And this guy here would map to that one. So maybe go like this. I'll go over here. Okay, so now we can change variables. So let me erase some stuff here. Okay, so I've written up here the change of variables formula for our guy. So this is the guy we're looking for. Double integral over a region of ln of x squared plus y squared dA. So using change of variable, it would be double integral over s, f of t, and this right here would be your f. So this guy will be your f of xy. Okay, so we need to find our t mapping, but we actually have it here already. So let me write it right here. So our T mapping, so that'd be T of R theta, just goes to our x, y, so it's going to be R cosine theta, R sine theta. Okay, and our S here is this rectangular region, so we're doing theta first, so it's going to be from 0, let me just change it right here then, so it'll be from 0 to pi over 2, and then the R goes from 1 to 2. Okay, so we still have to find our Jacobian and our f of t of r theta. So let's do that. So let me erase some stuff here. Okay, so if I erase some stuff, I put my t up here. So my t mapping, actually, this is x, and this is y. And now I have my Jacobian definition here. So it's going to be partial x with respect to r. So in this case, it's going to be cosine. And then partial x respect to theta, so it's going to be minus r sine theta. Then y, so over here, derivative of y respect to r would be just sine. And derivative of y respect to theta would be r cosine. So doing this, it'll be cosine times r cosine. Let's do it over here. So it'll be r cosine theta squared. Then that times that minus, but it already has a minus there, so it'll be plus. So it'll be r sine squared, and you can pull an r out. And it'll be cosine squared plus sine squared. This guy's 1. So it's just going to be r. So going back up here now, this guy, Jacobian is r. Okay, so let me erase this Jacobian now, and then we'll figure out f of t of r theta. So now, f of t r theta. Well, here's my f function right here. It's ln of x squared plus y squared. So in place of x, I'm going to put r cosine. In place of y, I'm going to put r sine. It's going to be ln of r cosine, the whole thing squared, plus r sine, the whole thing squared. That then you can write as ln. You can then pull an r squared out. It'll be cosine squared plus sine squared. That's 1. So it's going to become then ln of r squared. And we can bring that 2 in front if we wanted to here. I'll do that here. So it'll be 2 ln of r. That's going to go in place of this guy right here. So it'll be 2 ln of r. Okay, we've got everything we need now to do the integral. So let's start doing the integral now. Let me erase some stuff here. Okay, so we found our f was 2 ln of r, Jacobian r. So plugging those things in, we'll get this right here. So then integrating with respect to theta first. So it'll be then integral 1 to 2, actually let's put that 2 with this r here. So it'll be 2 r ln of r theta evaluated at 0 and pi over 2. Then dr will be then 1 to 2. So putting pi over 2 here. putting pi over 2 here, the 2 will cross off with this one. So it'll be then, and I can pull that pi outside the integral. So I'm going to pull it out over here. Because putting pi over 2 here, 2's cancel, then pull the pi out in front. So it'll be then r ln of r dr. Okay, so now I have to integrate this ln. So recall integration of parts, we're going to have to use that here. So integral u dv equals uv minus integral v du. So we're in this integral, I'm going to do the indefinite one first, and we'll come back and do the limits on it in a second. So I'm going to say let u equal ln of r. So then du dr equals 1 over r. So then du equals 1 over r dr. So then dv, so I'm going to integrate this guy, so the dv then would be the r dr. So integrating both sides, then we'll have v. So integrating here will be r squared over 2. Okay, so I'll come back to this. We're going to just do the indefinite integral r ln of r dr. Well, actually, I'm running out of space. Just erase a few things and come back. No, actually, I think I can squeeze it here. So let's see. So we're looking at integral of r ln r dr. It's going to be our u dv. So it's going to equal then uv. My u is ln, my v is this. So it's going to be r squared over 2 ln of r, then minus integral v. V is the r squared over 2 times du. du is 1 over r dr. Let me just out of the way for now. So the v, I can put it up here if you want. The v was r squared over 2. Okay, so r is cancelled there. So then it'll be r squared over 2 ln of r. Then integrating this, it'll be integral of r over 2, so it'll be minus r squared over 2, r squared over 4, sorry, because it'll be r squared over 2, so the 2 are there already, so it'll be r squared over 4. Okay, so we're going to have to then put this guy right here. After I integrate, yeah, I'll do the limit on it then. So let me erase a few things. Okay, so now I can make the substitution up here. So it'll be pi, then the integral of this guy is this. It's going to be r squared over 2 ln of r minus r squared over 4 evaluated at 1 and 2. Okay, so I'm going to put 2 in and put 1 in and work it out. Okay, so putting 2 in, 2 here, it'll be 2 squared over 2 ln of 2 minus 2 squared over 4. Then subtract, put 1 in, so it'll be 1 half ln of 1 minus 1 fourth. Okay, the ln of 1 is 0, so that's gone. Okay, so it's going to be then pi So it's going to be then, that's 2 ln of 2, that's 1, so minus 1, and it's gone, so it would be then plus a fourth. So then doing that subtraction, it'll be pi 2 ln of 2 minus 3 over 4. This is our answer here. Okay, so we're done.